Okay, we won't have to do that long process of taking derivatives for problems. Instead, we'll do most of the Maclaurin series that we find by using the 4 techniques that you had to on the last quiz. That is, substituting, multiplying by a power of x, or a constant in a power of x, taking the derivative, and possibly differentiating on both. Well, differentiating is taking the derivative and possibly integrating both sides of the equation. But now we have 4 starter sets. These are 4 series that we know. There's sine of x that we just found, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And cosine of x, you almost get that for free by looking back at the previous page. It turns out to be all the even numbers. Those are the ones that have a plus or minus 1 coefficient when you take the nth derivative and plug in 0 instead of the odds. And so it's n equals 0 to infinity, negative 1 to the n, x to the 2n divided by 2n factorial. And that's a series that will converge to cosine of x when you plug in x. Then there's the ones we know from before already. We have e to the x and 1 over 1 minus x. So here's and one more. That's kind of this one that we worked out before, but it's good to know as another one on the list. Natural log of 1 plus x. It equals negative 1 to the n minus 1, x to the n over n. All right. So a new topic. Those were Maclaurin series, and the key feature of Maclaurin series is that you have x to the n every time in the answer. And it's the nth derivative at 0 that you use. So a Taylor series is going to have x minus a to the n, and it's going to be using the nth derivative, plug in a. So it's exactly the same thing, but it's got a different center for the radius of convergence. And you use a plugged into the nth derivative, and you use x minus a, where a has to be a constant that you're given. So the reason that this is useful is that it's good for approximating f of x near x equal to a. And for the Maclaurin series, those are good at approximating f of x near x equal to 0. For an example, approximate e to the x near x equal to 2 to the n equal 3 power of x. Use it to find e to the 2.1 approximately. So e to the x, this is now the nth derivative of e to the x is pretty easy to work with because it's just e to the x since it's its own derivative. But we're supposed to put in x equal to 2. So when we take the 0th derivative, that's e to the x again. And then you put in 2, it's e squared divided by 0 factorial. Then the first derivative is also e to the x. Put in 2 again, so e squared. And that's going to happen every time. The nth derivative at 2 is always going to be e squared. But then you have x minus 2 to the 1 divided by 1 factorial. X minus 2 squared divided by 2 factorial, x minus 2 cubed divided by 3 factorial. And that's going to keep going forever, but we said stop at n equals 3. So that's the n equals 3 power. I should point out that if you look in Calculus 1, Chapter 3.10, there's something called linearization. And that's when you say that the function is approximately equal to the function value at that point plus function value at that point, the first derivative at that point times the difference in the x values. And yep, that's exactly what we have here. When you just take the first 2 terms of a Taylor series, it's exactly the same thing as linearization from 3.10. So what the Taylor series can do is extend this linearization, where in linearization you replace the original curve with the tangent line. A Taylor series can then replace the original curve with a parabola, that's the x squared, or with a cubic, the x cubed, and approximate it better and better and better the further you go out. So the next part of the problem was to find e to the 2.1. So then I plug it into that original, that previous line, and I have x minus 2 every time. So that would be the 2.1 minus 2. So it's just 0.1. And e squared every time, I just went with 7.389 for that. And so it's 7.389 plus 7.389 times 0.1 to the 1 plus 7.389 times 0.1 squared divided by 2, that was the 2 factorial. And then 3 factorial is 6, so the next one is 7.389 times 0.1 cubed over 6, which comes out to about 8.166.